Okay. Okay, so just give you a chance to think about where we ended last time. So I'm showing you the vector field that's showing now is force field 1, F1, negative XX. And then we have 3 segments, and we're gonna go. Let's see here. And we're gonna go from 0, 1 down to 1, 0. So our starting point, say A. There it is. Okay. Come on. There we go. All right, so we're going to go from, so this we'll call this, say, point A, and that's 0, 1, and then point B is 1, 0, and we're going to look at three line integrals along C1, the unit circle, C2, the straight line segment, and C3 is 1 minus radical x. So without doing any calculations, so I'm not asking you to find these line integrals, but if we're in, say, vector field 1 here, F1, negative x, comma x, what could you say about these line integrals? What could you say about these line integrals? So everyone's talking to somebody, find a partner. What can you say about those line integrals in force field or vector field number 1, negative x, comma x? Find someone to talk to about that. Talk about with vector field 1, negative xx, comparing these line integrals, or any observations about these line integrals in vector field 1.
It's not a gradient.
Okay, Trevor says not a gradient field. Agree with that?
Yeah.
Okay, they like it. Anything else you guys talked about?
And that meant like the line integrals way you cancel each other out would be like 0, I believe.
Okay, so we're talking about just all of them starting here and ending here.
Gotcha.
So if we were say to compare the red line integral to the purple, it's like C1 line integral to C2 line integral.
They wouldn't be the same.
You're saying they wouldn't be the same? Okay. Is there anything you can say about them? Yeah.
Negative?
He's saying they're negative. Are these line integrals negative? Going against the forces, right? So it's kind of like putting work back into the field. If it's a force field, it's kind of like whatever's traveling this path, it's like putting work back into the field. So that's the field doing negative work. The field doing negative work. Okay? Any other observations? Okay, so if we were to, this is kind of what we said, if I was to say change the direction of the purple one and head back. So now that makes a loop, right? That makes a loop. I'm going to head down the unit circle to point B and then back up the straight line segment to point A. What could we say about that line integral? Call that C4. What would that line integral? What could you say about it? Still going to be negative?
Maybe positive. Looks like it's going to be positive. That straight line looks more inline.
Okay, but what do we know for sure? So not 0, right? Why is it not 0? So actually, it might be 0, right? You can have a loop in a non-conservative vector field that ends up being 0. It's just probably it's not, right? Probably. If this is if the integral for C1 was different than the integral for C2, if we know those are different negative values, then the loop will not be 0, right? Because now this is positive and a different positive than this is negative. So that loop down the unit circle and back up the line segment will not be 0. given that those two original ones were not equal. Okay, does that make sense? Okay, so I'm going to show you a different way, rather than, like, so every time to determine this was not conservative, we just like tried to find the potential function, and if it didn't work, we said it was not conservative, right? So I'm going to show you a different way to check whether it's conservative or not. So if this were conservative, what are these values again? This one is, what is it? This one's the partial with respect to x, right? And the second one, the y component is partial with respect to y. Do you remember what we said about there was a relationship between second partial derivatives? Do you remember? We didn't. Well, there's 4 second partial derivatives, right? There's fxx, fxy, fyx, fyy. There's 4 second partial derivatives. So do you remember the relationship that we had? Yeah. Sorry, you got drowned out. What?
fx, y, and fyx are equal.
Right. So if you start with a function f and you take the second partial fxy and the second partial fyx, those are equal. That's Clairaut's theorem. So this is a really fast way we can check, right? So if this were fx and if this were fy, then what would be true? This one, we would do what? Take the derivative with respect to y, and that would be, then we'd have fxy. And we do this one and take derivative with respect to x. And then if this was a gradient field, then what would be true? It'd be equal. So what is f? So we don't know for sure if there's an f, and if this is fx, and this is fy, but we're just kind of pretending, right? We're pretending this is fx, pretending this is fy, and then as we keep pretending, then what is fxy? Oh no, 0, right? Yeah. And then what's fyx? 1. So is this fx? Is this fy? Is this fxy? Is this fyx? So what's happening here? Are they equal? No. So all this pretending was wrong, right? All this pretending that we had a partial with respect to x and partial with respect to y, and that these were the second derivatives, it's just not true. There's no potential function f in the first place. So that's confirming what we decided visually, right? Confirming that this is not a conservative field. So with conservative fields, we have what? They're gradient fields. What else do we know? Path independence, right? Path independence. So if you have the same starting and ending point in a field, and the path matters, gives you a different line integral, you don't have path independence. You have path dependence. It's dependent on the path. Okay, what else? So path dependence means that so what we're going to call circulation, so this integral down the red circle and back up the purple, that is called a circulation line integral because it is a closed loop. So in a gradient field or a conservative vector field, what do we know about circulation integrals? Yeah, they're going to all circulation integrals will equal 0. Okay? All right. In a non-conservative vector field, could you have a circulation integral equal 0? Yes, but all it takes is 1 that doesn't equal 0, and it's not conservative, right? So you can find as many zeros as you want, but if you find one circulation integral that's not 0, then you can conclude that it's not a conservative vector field. All right, and now we have a fourth thing about this, is that in a conservative vector field, your second partials would equal, by Clairaut's theorem, fxy would equal fyx. So everything we've talked about with this first vector field confirms that it's not a conservative, right? We did not have path independence. We have a circulation integral that's not 0, and these pretend second partials not equal, right? Not equal. Okay, so now let's look at vector field 2, 1, comma y. I'll show that one. Oh, so now is the vector field, or is the integral from a to b, is it always negative? Is it always negative? Oh, I got you there. Is it always negative? What's that? Okay, but is it always negative for all paths? From A to B. Will the line integral be negative?
Yes.
Okay, now answer. So I want you to come up with a path where the line from A to B. Can you come up with a path from A to B where the line integral is 0? And can you come up with a path where the line integral is positive? So see, starting at A, ending at B, draw a path, or imagine a path, where the line integral will be 0 or close to 0, and then a path where it would be positive.
Can you? F1, or are we on F2?
What's that?
Are we on F1?
Still on F1. So I'm showing you F1 still. This is negative XX. This is negative XX. So compare with each other. Take a minute. So create a path so that the line integral from A to B is about 0 and positive. Another one that's positive. You gotta leave, you gotta leave. Okay, let's do, anyone come up with one that's 0? Who thinks they're, David?
If you go down the y-axis,
Down the y-axis.
and then you go perpendicular to the
So tell me where to stop. So I'm going to head this way. What's my accumulated line integral through here? 0. How far should I go?
there.
About
To 1.
to 1, and then
And you go like,
straight back.
to B, yeah.
What do you think? So all along there, 0, and then if you head perpendicular to the vectors, still 0. Anyone come up with a different way to get 0? Yeah?
If you were to go in the top left-hand coordinate, and you were to go down into the origin,
Okay, down to the origin.
like let's just make any type of path in that third coordinate down to the origin. If you were to make that same exact path in the bottom right-hand coordinate to B, wouldn't that kind of equal 0?
Oh, okay. So he's saying whatever you do along to there, do the same thing symmetrically to there.
Yeah.
What do you think? Yeah, exactly. Because this will be positive here, and then by symmetry you have the same negative contribution going back. Yeah, nice job. Yeah, Eric.
You go orthogonal in the quadrant 2,
Okay.
negative 1.2, or negative 1, sorry.
To negative 1 to here.
Yeah, and like go straight across and then they'll cancel out.
Oh, nice. Okay, so this would be all 0 here. Then we'd have some positive contribution to the integral, and then the same negative contribution to the integral across like that. Nice. All right, what about positive? Somebody new. Come up with a path that'll give us a positive integral. Think you got it or no?
This was a random path I thought that you could go like really up among the first quadrant, so you can positive, and you go down into the second quadrant, and then you make a quick right. And then you get
So you want to head up the axis,
no, it's slightly right than that.
slightly right, and then you're getting some positive. Okay.
And you go to the other side of the axis and go all the way back down, and then go to the right. And you overall positive.
Oh, you want to make a little bit positive here, go back to A, and then make 0. Is that kind of something like that? Yeah, that'll work. Yeah, it works. So yeah, just do something up here that gives you a little positive, getting back to A, which would be like just into the first quadrant and then back down the axis, and then any one of those 0 paths to B. That's great. Sure. Any other ideas? Yeah.
Go into quadrant 2 all the way to -1, 0.
Okay.
And then go down to 0, -1, and then back up.
Yeah. So if you just do a diamond, it'll be 0, and you get all this positive, and then back 0 again, and then so the total will be positive. Okay, so we get the idea. So right, so definitely not conservative, because to get from A to B, we have negative. We got ways to do it to get negative line integral, 0 or positive. Okay, so now back to zoomed in version, and let's try the other one, 1y. Okay, so 1y, let's try our Clause's theorem. If this were the partial with respect to x, then what would we do? Take that with respect to y and you get 0. And if this were the partial with respect to y, we want to do what to it? Take the partial with respect to x and we get, conclusion? Equal, right? So fxy equals fyx, and there is a potential function, right? So that's, for these R2 vector fields, it's a nice quick little check to see if you have a gradient field or not. Check fx, suppose that it's fx, fy, and check fxy versus fyx. Okay, so what does it mean about the line integral for C1, C2, and C3? The line integrals will be equal, starting from point A to point B. And if I make a loop here out of these, so if this line integral going down this way is equal to this line integral going this way, then what can you say about the line integral going back? What can you say about this compared to this? Equal and opposite, right? Equal and opposite. Therefore, that's why every closed loop is 0, right? So so there's this very easy connection from path independence to all circulation integrals being 0, because if every path has the same line integral, all you do is take one of those and flip it the other way, and now you have the opposite, and you've made a loop, and now it's 0. Okay. All right, so can we find an integral from A to B that is 0? So first of all, what can you say about these? What would you say in terms of negative 0 or positive going from point A to point B? We know they're all equal, but are they equally 0, equally positive, or equally negative? Oh, I got you there. I think the blue one is the easiest one to see. The blue one is the easiest one to see. Negative or positive? Tell me what's going on here. Very slightly, but through here, 0, and then what about all this? What do you think? Positive. Look at all of this, starting about here. All of this has positive contribution from the force field, or the vector field, right? Maybe not much, right? But so you got a little component there, and then here you have big components, right? The big components of these vectors are positive. You see that? So a teeny little bit of negative at the start, then you have a kind of a 0 through here, but then starting there, you have all positive components of the vectors in the direction of the path. Definitely positive. Okay, and then that would be true for any, so we could do all kinds of crazy paths through the third, fourth, and fifth quadrant, no, second, third, and fourth quadrant to get to B, and we'll always get the same positive value. In fact, I think they're all equal to 1/2. So all those line integrals are equal to 1/2. And so you can check that later. You know, you've got this function, you know how to parameterize a straight segment, you know how to parameterize a circle, you've got the field, you've got the vector field, so those are easy line integrals, and you can confirm that they're all equal to 1/2. Okay? All right, so let's talk about, let's do another problem. Let's do an R3 problem. So Frodo is on his way to deposit the ring into the depths of Mordor, right? Okay, and so here's where Frodo and Sam are now. And they got to make it to the Death Lake or the fire, whatever it is. Throw the ring in. If you don't know what I'm talking about, don't worry. But here's how they're going to go. They're going to go on this. Here's the surface, fxy. And they're going to walk this path. And Sam says, I can't carry the ring, Mr. Frodo, but I can carry you. All right, there we go. And so this is the path we're going to take. And we need to find, and the force field is gravity. So what is that? What is the x component of the gravity field? 0. Y component? 0. And the z component is negative. The mass, g, right? Is that it? Force is just, negative mg. That's right. Okay, and so, let's see. Together they weigh 75 grams. Kilograms. All right, so we say. So, let's see. Frodo, Sam have combined mass of. They're little guys, right? How much work does a force field do when they walk that path that I drew? And so then we can specifically get what the force field is for them, for Frodo. Sam carrying Frodo would be 0, 0, what? Negative 75. And we'll just assume the same gravity field as Earth. Yeah, I don't know what the gravity field is for Middle Earth, so we'll just go with the gravity field for Earth. Okay, and so this is the force field that they're walking through, and we need to figure out, and this is, the starting point is negative 0.5, negative 0.5, 0.01, and 0.85, 0.65, 0.98, and these are all in kilometers, all these dimensions in kilometers, from some reference point 0, 0, 0. So this, and we need to find what's the work, how much work does the force field do along this path to get up to that point. Okay, so I want you to figure out how you're going to solve this question. Figure out how you're going to do this with what we know so far. So with what we know so far, you need to figure out how to find the work the gravity field does as Sam carries Frodo from the blue point to the red point. What is the key to being able to do this with what we know so far? Julia? What? Okay, for what purpose? Let's keep. So if it were conservative, then
no matter what path they took through the mountains, the overall work would be the same.
Okay. So how does that help us? She's saying, is this a conservative? What's that?
You can just make a vector.
So instead of a vector, I think what you mean is, what do we want? What's that?
That straight path.
Yeah, that's right.
Yeah, so we want to just go straight. And it doesn't matter that they're not on the mountain anymore, because if it's a conservative vector field, then the straight path from that point to that point will give us the same line integral. So hopefully you got that far. Did you get that far? All right, so what do we need to do to that? So instead, we're going to take this So we're not going to go on this horrible path and use this horrible function to define that, but we can just go, not like that. That's supposed to be straight. There we go. That's better. Wow. Really bad. Okay. Yep. So we're gonna take the straight path, and so call that C. So how do we need to define the straight line path. Okay, but we need to parameterize a path. We need a vector function. It's not just a vector, right? We need a vector function for all those points along the path. How do we do that? The easy way. Yeah, what's the initial point?
0.85, 0.65.
So negative 0.5. Negative 0.5. Is that a hand over there? Yeah, Alex.
Wait, why do X and Y matter?
What's that?
Why do X and Y
So we can practice doing an R3 line integral.
Oh, yeah. Got it.
So in case you don't see what you see, we just want to do it the whole thing. Okay. Yeah, but good observation. X and Y will not matter in the end. Okay. Okay, so we can do the starting point. This is this thing I showed you last time. And then what will the x be? Negative 0.5, what? Plus 0.85t? Just remember what the coefficient of t should be? So when t is 1, when t is 1, we need to get what value for the x? You answered both questions, actually. When t is 1, what does the whole thing need to be?
The end point.
0.85, right? 0.85. Therefore, what do we want to put there? I don't get 1.3, guys. Oh, you're right. I was thinking it was 0.05. Okay, good. So it's going to be plus, how many t? 1.35t. Okay. Because now when t is 0, we get negative 0.5. When t is 1, we get the 0.85, right? Okay. Good thing you guys are here. All right, so negative 0.5 plus, what's the next one? 1.15t. Finally, 0.01 plus 0.97t. Okay, so there's our r. And so what's our dr? We're going to need dr to do the line integral. That's easy. 1.35, comma, 1.15, and 0.97. And so now we can write, the work done by the vector field is the dot product for the integral, right? The integral for our path C of f, which is the 0, 0. Anyone solve that? What is that? Negative what? So this is their force in newtons. Negative 75 times 9.8, negative 735. Okay, someone said something about converting. Do we need to convert something? Right. So let's leave that one. And how do we need to convert our r and our dr? So these are all in kilometers. So you're going to divide by 1,000? multiply by 1,000. If we want to get all this stuff in meters, we have to multiply. We're going to multiply by 1,000. So times 1,000. And that gets all our dimensions for the R function in meters. So then we're going to have dot 1350, 1150, and 970 dt. Okay, so that equals integral from, what's our limits on t? 0 to 1, because of the way we set up the line segment. 0 to 1 of what? That 735 times. So all that matters here is the z component. dt, which just ends up equaling that number, that negative number. So negative 735 times, I get that. Is that right? Negative 75 times 9.8 times 970. So that's joules. So let's put it back into kilojoules. So negative 7, I don't know, let's keep it in joules. So what is this? This is the work that the force field, the gravity field, does on our heroes as they climb up the mountain. So how much work does Frodo do? How much work does Frodo do climbing this path?
7,000.
The positive version, right? So no, Sam's doing the work, right? Sam exerts positive 712,950 joules to carry Mr. Frodo. And we have path independence. So if he would have walked all the way down here and then up this way and then down there and then like this, it's still, so the energy that the gravity field would have given him going down would have all canceled out, so that he exerts the same amount of work to get from there to there, no matter what the path is. That's why we could choose the straight line path through the air, right? Through the air. Okay, questions on that? Questions on that? Okay, so there's something called potential difference. Okay, so the potential energy that they have here versus here. What's the potential energy they have here versus here? So potential energy is mgh, right? So the change in potential energy of our heroes is what? Potential energy final minus potential energy initial. So what's their final potential energy? M is 75 times 9.8 times, what's their height right now?
Final.
10, right? Oh, final. Final is, what, 980? Is that right? 980 meters up. And their initial is 75 times 9.8 times 10. So what was the change in potential energy of their final position relative to their starting position? Same thing. Okay? What is this, are they in a conservative vector field? If they have a conservative vector field, that means it's what kind of field? Gradient field, which means there exists a potential function. Find the potential function for this gradient field. Find the potential function for this gradient field. Go. So what's the potential function that has this as its gradient? So what's the potential function that has this, or a potential function that has this as its gradient? In other words, what is f? X, y, z. So this is going to be a multivariable function of 3 variables, right? Since we have 3 components to the gradient. So what is it? Negative. Just 9.8? Negative 75 times 9.8 times z. Plus a constant. But so what do you notice about that potential? That's what? That's m, g, h. So why have we been, so look, why is it called a potential function? Because it's the same function as the potential energy, right? It's the potential energy function for this force field. So notice that this vector now, this line integral that we did is the same as, so that line integral that we did, f dot dr for c, equaled what? We took the potential, we found the potential final, which is really what? Is the value of the function where? At the final point, right? This was f final. Minus, then we did the potential energy at the initial point, which is this is our potential function, right? Minus f initial. So this is an alternate way to find, rather than doing the line integral directly from there to there, we could have just found the potential energy or the potential function and found the net change in potential energy from final to initial point. And that's, all kinds of bells should be going off here. Oh, I know what that is. I know what that's just like. What's that just like? Because I'm a calculus expert. What is it? Yeah, this is the fundamental theorem, right? So this is the fundamental theorem of line integrals, right? So now we have a line integral of a vector field, and so this is Fatoli, which is not some kind of Italian dish. It's the fundamental theorem of line integrals. Fundamental theorem of line integrals, which says that the line integral of a gradient field, so this would have to be a gradient field, equals the value of the potential function at the final point, right? Or their potential energy at the end, minus the value of the potential function at the initial point. And so that F right there has to be what? So for this to work, that capital F has to be what about F? The gradient of F, right? It's the gradient. That field is necessarily the gradient of F. Okay. Did all that make sense? Did I lose you? This is really important. Okay, so let's go back to the 1 comma y. So now we have a new way to find that line integral. Remember we did all those we had those different paths. I'm gonna leave this. Can I erase this now? This very important screen. Everyone got it? Any questions? Okay, so now let's go back to this one, and we're on field 2, 1 comma y. And I told you that all those line integrals were 1/2, and those are all easy line integrals you can do. So now find another way to confirm that those line integrals are 1/2. What's another way to confirm that those line integrals are 1/2? Instead of doing a line integral, you could do what? Go. What's that?
I was thinking about F final
Okay. So when you say f, what kind of, you mean this f? So we're going to do this at the final point minus this at the initial point. So, Paul.
Plus the gradient.
Right?
Lowercase, so you need to find a function that could give that.
Okay, did you get that?
It's like a x plus y squared over 2.
Yeah, so this is the gradient field of some function f, right? And so you came up with?
Okay, f of xy equals x plus y squared over 2 plus a constant.
Yeah, plus any constant, right? So that's our, what? That's the potential function. And we know having the potential function, we can find that line integral a different way. So this is our point A, point B. So it would be, what would it be then? So just generally the expression?
F of 1, 0 minus f of 0.
So f of,
1, 0.
yeah, b, right? Minus fundamental theorem, right? Fundamental theorem. This is, and this what? So this f is something of an antiderivative, right? So this is the gradient field. That means what? It's like the derivative of f because we take the partial derivatives to get it. So then this potential function is something of an antiderivative of the vector function. So what is f of b? It would be f of 1, 0 minus f of 0, 1, and f of 1, 0 equals 1. F of 0, 1 is a half. So do the math, put 1, 0 into this, put 0, 1 into this, and we get a half. Okay, I got a summary screen, so just hold on 1 second. I want to get done the video. So don't try to copy it down on what I'm about to do, but it'll be on the video so you can copy it later. Questions on this example? Does it make sense? Doesn't make sense. So just a quick visual of that. So here's that vector field in the xy plane. And so here's the point 1, 0 and 0, 1. So any path through that vector field, so taking any path through that vector field to get the line integral from there to there, it's going to be the same as what? The difference in height of that surface. So this is x plus y squared over 2. So the difference in height of that surface will be the same as any line integral from that point to that point through the field. That's what the fundamental theorem says. Summary. Here we go. So just pay attention and write it down later. So all these statements are equivalent. If any one is true, then all the rest are true. First is f is conservative vector field. If that's true, then f is a gradient field. So f has some function, potential function f, such that our vector field is the gradient of f, right? We have Clairaut's theorem. If f is pq, then py equals qx, right? Because our fxy equals fyx. Every circulation integral in a conservative vector field, right? Circulation integral meaning, so this is how we're going to stand for circulation integrals. Integral sign with, I lost my pen. A little circle on the integral sign means a closed loop that we're going around for c. We're going to get 0. Path independent. Given any 2 points in A and B, to go from A to B, you'll have the same line integral to get from A to B. And therefore the fundamental theorem holds that the line integral is the difference in the values of the potential function at the end and the beginning, just like the fundamental theorem you've seen before.